This is A21 Module 4 January 10. Unfortunately again I've got the answers written in here, so I might do some of them out on a blank sheet of paper, the calculations anyway. This is a question 6. Define the half-life of a radioactive sample. And a half-life is a length of time, and it's the time taken for the activity of the sample to have dropped to a half, or the number of radioactive nuclei in the sample to have dropped to a half. But you always must say that it's a length of time. Part 2. A geological rock sample contains 2 radioactive isotopes X and Y. The half-life of isotope X is twice that of Y. In the sample there are N nuclei of X and 3 N nuclei of Y. After 2 half-lives of isotope X, find the ratio, number of nuclei of Y to the number of nuclei of X remaining in the rock sample. Okay, so we're going to start off with what I've done here. Is the half-life or the radioactive constant, so part 2 here. So we'll just read the information again. A geological rock sample contains 2 radioactive isotopes X and Y. The half-life of X is twice that of Y, so half-life of X is twice that of the half-life of Y. In the sample, there are N nuclei of X and 3 N nuclei of Y. So the number of nuclei of X is N, and the number of nuclei of Y is 3N. After 2 half-lives of the isotope X, find the ratio, and then the ratio is the number of nuclei of Y to the number of nuclei of X. Now, the first thing I've done here is I've written down an equation, and the equation is for, let me see, it's for the decay constant. So the decay constant of X is going to equal 0.693 over the half-life of X. But in terms of half-life, that is twice that of Y. And so I'm going to call the half-life of Y T. And so T the half of X is 2 times T. And so that's equal to 0.693 over 2T. Then the radioactive decay constant of Y then is just 0.693 over T. So we've got 2 equations there for that. I'll just scan out a bit so you can see it better. And then the next thing I'm going to do is I'm going to write down N equals N naught e to minus lambda T. For Nx, so Nx is equal to N naught e to the minus lambda T. But the N naught for Nx started out as N. I should have put in a little naught there. And so I'm going to rewrite that again. Nx equals N e to the minus. Now lambda is 0.63 over 2t for x. You can see up there. And the length of time that's halved is 2 times the half-life, which I called t. So that's 2t there. For ny then, ny started out with a total number of nuclei of 3n. E to the minus, there's the decay constant, 0.693 over t. And the length of time that's passed again is 2 half-lives or 2 t's. And so the equations then go down then to nx equals n e to the minus 0.693 because the 2 t's all cancel each other out. And ny over here goes down to 3n e to the minus, and it's 2 times 0.693 because the 2 t's cancel each other out there. Have I written that down? I haven't written that down, so I'm just going to write 2 times by 0.693. And then we're going to compare the ratios of the 2 of them. And so nx over ny is equal to n e to the minus 0.693. And that's divided by 3n e to the minus 2 times 0.693. And the n's cancel each other out. And so we eventually come down to then 0.75 divided by 0.5. Sorry, other way around. 0.5 over 0.75. And we're actually being asked for the ratio of y to x, and so I need to turn that upside down. So the ratio of y to x is equal to 0.75 over 0.5, and that's the same as 1.5 to 1. So ny to nx is equal to 1.5 to 1. That seems very long-winded there. There was quite a lot going on there. But that's the way I tackled that, to write down the two equations that I ended up with and then take the ratio of them. I actually took the ratio of nx to ny, but the answer was looking for it upside down. So if you did do it the same way as me, then just turn it upside down at the end, and there's your answer at the end there, just at the very end. Right, part B then. Polonium is radioactive and emits alpha particles. A mole of polonium has a mass of 210 grams and its decay constant is 5.8 by 10 to the minus 8 seconds. Calculate the radioactive activity of 1.5 milligrams of polonium. And again, we haven't got much space here, and I've already written it, so I'm going to do it out on a file page again. And so one mole of polonium has a mass of 210 grams and its decay constant lambda is 5.8 by 10 to the minus 8 seconds. So it says calculate the radioactivity of 1.5 milligrams of polonium. So the first thing we have to do is to see how many atoms we've got. So the number of atoms is going to be equal to, we know that 210 grams gives us 6.02 by 10 to the 23, Avogadro's number. And so it's 210 divided by 1.5 milligrams, so that's by 10 to the minus 3, and it's multiplied by 6.02 by 10 to the 23 atoms. And that gives us 4.3 by 10 to the 18. So that's 4.3 by 10 to the 18 atoms. That's in our sample of 1.5 milligrams. And so now all we have to do is A is equal to lambda n. And lambda is 5.8 by 10 to the minus 8. And n is 4.3 by 10 to the 18. And that gives us an answer of 2.49 by 10 to the 11 becquerel. Last question, how many nuclei of polonium remain after 65 days? So you're now going to use your, this is part 2. N is equal to n naught e to the minus lambda t. We're looking for how many nuclei remain. We know the initial number is this number here, 4.3 by 10 to the 18. We know that lambda is 5.8 by 10 to the minus 8. And we have to change our time of 65 days into seconds. And so therefore that's 65 times 24 hours times 3,600 seconds in an hour. So that's a big calculation you have to do there. And when you do that, your answer comes out to be 3.1 by 10 to the 18 atoms.